Hi, and welcome to Module 5 of Lecture 2. Module 5, and from now on in this lecture, we're going to get going on particular applications of all the ideas we've been working through and building up over the past bunch of modules. I'm going to start by providing general rules for how to go about hypothesis testing. And a lot of this is going to be bringing in stuff we talked about before, but in a more concrete fashion. So before we mentioned comparisons and how comparisons were central to this process of hypothesis testing, we're going to consider two kinds of comparisons. One is very much in line with the treatment and control idea, which is we can compare sample estimates between two groups and try to see if there's a difference between, say, the sample mean of one group and the sample mean of another group. Think of that as, say, treatment and control groups. The other kind of comparison is to compare a single sample and, say, a sample mean from that sample to a hypothetical parameter, often 0. The key here is, for hypothesis testing, is we can't just look at differences between the numbers, between the groups, or between the single sample and some hypothesized parameter. It might be that a difference is really big because there's a real difference there that might support some theory, or it might be that the difference is big due to random chance. Because, as we discussed last couple times, all these things we're dealing with samples, all these parameters we're measuring are random variables, and they have uncertainty associated with them. We have to take into account the fact that differences could be real or could be due to random chance. And in fact, most of what we're going to be doing here from now on in this lecture, at least this lecture part 1, is going to be trying to figure out for different types of data how to set up a mechanism to be able to reject the null hypothesis given different kinds of data. So reject the fact that you might have big differences due only to random chance. So to reiterate our earlier hypothesis generation, we said there are two general kinds of hypothesis that we care about. H1 is the research hypothesis. It's the difference between the groups, or the difference between the sample and the hypothesized parameter that we expect to see given the theory that we're working with. The null hypothesis is the statement that we will not see, that we don't expect to see these differences, or that any differences we do see are the result of random chance. So connecting to it earlier, right, H1 is we expect to see X increase Y, or changes in X lead to changes in Y. And the null was we expect changes in X to have no relationship to changes in Y. In practice, given that these are random variables, we will see probably almost always some change in X that have some change in Y associated with it in some sample. We want to see if that change is meaningful or just due to random chance. Our goal is always, though, no matter how we phrase this, is to reject the null hypothesis. We are trying in this case to reject the possibility that the differences we see in our samples are due to random chance only and not something deeper. This may seem pretty weak, but again, the goal is to help out with incremental science and over time reject the possibility that we are just seeing random chance and provide support for theories with multiple hypothesis tests over time. Okay, so we're going to offer a 5-step model for this. In the first step, we're going to make some assumptions that let us do the later steps, and ideally determine if the assumptions are met and not just assume they're true. The primary one here I want to focus on is we're going to assume random sampling. We're going to assume that the sample that was chosen from the population was chosen at random. So we can use things like the central limit theorem to get nice properties of the sampling distribution, as we discussed earlier. Notably, that the sampling distribution will be normally distributed and have a mean equal to the population mean with a specified standard error. Now again, that might not be true in practice. It's often not true in practice. A lot of what you'll be doing here in this step is trying to justify that what you have is close enough, or its violations aren't too substantial. In step 2, we're going to state the null hypothesis. This is typically a hypothesis that says, okay, if the research hypothesis is the mean from group 1 is different from the mean from group 2, there's no difference between the groups. It would be the null hypothesis. The only variation here might be situations in which you have a directional hypothesis, in which case, if the directional hypothesis says increases in one variable leads to increases in a different variable, you might then have a null that's the opposite, which is increases do not lead to increases, which mean they could be nothing happening or it could be decreases. So these are all possibilities, but in general, the null hypothesis is just there is no difference, and we'll go through some more examples later. But if there was one thing to remember here, it's the null hypothesis is there's no difference between the groups, or there's no difference between the hypothesized parameter and the sample mean of the sample. Okay. Once you've done that, and these are all sort of theoretically driven, except for one where you try to show that your assumptions are true, you then have to determine the sampling distribution and the critical region. Now this is all determined by what kind of data you have and what's your data generating process, as we discussed briefly last module. In general, you're not expected to come in just knowing all the possible sampling distributions and how you calculate all critical regions for any possible data generating process. Instead, we rely upon existing work to slot our particular analysis into a particular type of sampling distribution that exists already. And in this lecture, we'll go through 3 different examples for 3 different kinds of data. So I'm going to bracket this question for the point number 3 for now and go through it again and again for each one of these 3 examples we do during this lecture. Once you've determined what the sampling distribution is and its associated critical region, and I'll define critical region again also a little bit later, you calculate your test statistic. You calculate a particular statistic that's going to be distributed in some fashion, and we're going to try to see if that statistic is big enough, basically, to reject the null hypothesis. How big it has to be and how to calculate it would depend on the kind of data you have, and we'll go through details of that again in future modules. But that said, the key is you're going to be calculating from your data some test statistic and then comparing the test statistic to some critical value to see if that test statistic could have arisen via random chance given the assumptions inherent in the null hypothesis. Before I go into anything else, I want to take a step back here and try to make that last point super clear. So think of a simplified example in which the null hypothesis is that the mean is 0. That the mean of some parameter in some population is 0. Right? That's often a common null hypothesis, right? There's nothing happening here. The mean is 0. Then we might calculate a test statistic that incorporates the value of the sample mean and some measure of the error on that mean, on that calculation of the mean. The bigger that statistic is, and that'll be bigger in general when the sample mean is higher, further away from 0, and it'll be bigger when the error on that sample mean is smaller in general. And we'll see examples of that to make that clearer in the future, but take my word for it now. So as you get less error or a larger mean calculation, you're moving further away from 0. The idea is any number, for most of the stuff, any number is possible given a random variable, right? I might just get super lucky or super unlucky, depending on your point of view, and draw numbers that give me a giant sample mean. However, as I have a better estimate of my sample mean, the chance that I drew a really big number, despite the fact that the true value should have been close to 0, should be smaller, should get small. Think back to those examples we gave and looking at the central limit theorem, where we had larger and larger samples, and the sampling distribution shrunk very close to the mean. And all the examples from the samples we took were all very close to the mean. The more we get closer to that situation where the sampling distribution is narrow and the standard error is small, the less likely it is, probabilistically speaking, that a sample we drew from that particular kind of distribution with a mean actually at 0 could have produced a number as big as we got. So a more concrete example, even than that. Let's say the true mean is 0, and the error on our sample estimates is 0.1, and we got a sample mean of 4,000. There's extremely small chance that 4,000 came from population with a true mean of 0, given that error on our sample mean. Right? It can happen. It's within the realm of possibility, but the chances are extraordinarily small. In that case, we're going to say, okay, you know what? That's not likely to have come from that population with mean of 0. Probably we didn't actually have a mean of 0, given what we got in our sample. That's what we mean by rejecting the null hypothesis. We're going to be assuming the null hypothesis is true and seeing if the data we got is consistent with that truth of a null hypothesis. If it's too far from that truth, which we're going to figure out by calculating a test statistic and comparing to some critical value, as we'll discuss later, but if what we got in the sample is too far from the truth of that assumed hypothesis, of the null hypothesis, we're going to reject the null hypothesis. And that's step 5. We interpret these results and try to see if we can reject the null hypothesis or not. If we see a rejection of the null hypothesis, we say there's a statistically significant relationship between our variables of interest, and we get support for our theory. And that's how it works. And all we're going to be doing from now on is providing additional examples of this, concrete examples for how this all works with different kinds of data. But if you get this, you're doing great. If you don't get this yet, that's okay. We'll have more discussion of it over and over again, but it may be worth to go back and watch this particular slide again and see if a couple of iterations help this stuff sink in, because this is the real key for everything we do from now on. Okay. So I keep saying types of data that matter. Why does that matter? Well, it turns out the level of measurement for independent and dependent variables affects the kind of tests we can run and the kind of test statistics we can calculate and the sampling distributions we use. So in a rough sense, we have on the rows here the type of the dependent variable, and on the columns we have the independent variable type. And we have two kind of types in each case: categorical variables, right, which have categories like nominal or ordinal variables, or continuous, like interval ratio numbers. And then we check to see where our data fall. If our dependent variable is categorical, and so is our independent variable, we're going to be using what we call tabular analysis and analyzing with the chi-squared. You can see up here in the sort of summary area, the chi-squared, that's the lowercase chi, it's a Greek letter. The chi-squared is going to be a test we use for, and a distribution we use for the categorical independent variables with categorical dependent variables. If we have continuous dependent and independent variables, we're looking at correlations between the variation in the independent and dependent variables. That we'll do next. We'll do that second over here. You can see up here in the slides that that's the next thing we're going to do after that. And then finally, if we have a independent variable that's categorical, so we have treatment or control, for instance, 2 categories, but a continuous dependent variable, we're going to use difference of means. We're going to compare the means within of the dependent variable within each of the samples and see how different they are. Okay. In general, again, all these things, and the goal of all this is to reject the null hypothesis with a certain degree of confidence. This confidence is key to the scientific process, right? We're trying to assess a certain level of confidence, maybe to share that with others so they will know how confident we are in our estimates, and this confidence has to be quantified, not just a statement of our belief and how confident we think we are. So these hypothesis tests will approximate this confidence in our hypotheses. So we're going to structure them around the null, as we said. We're going to say there's no relationship between some x and some y. And we're going to try to falsify that statement of no relationship, right? So basically, we don't try to prove our original hypothesis, our research hypothesis is correct. We falsify that as incorrect by falsifying the null hypothesis. Again, that may seem a little backwards, but the idea is it's much easier to falsify in this case to show that a particular thing isn't likely to be true than it is to show that this thing is true, because there are always other possibilities that we might not have taken into account. By falsifying alternatives, we reduce the space of possible alternatives that could be true, and thereby provide additional support for our theory itself. So this test, again, is to compare the actual relationship between x and y in the sample to what we expect to find if they're unrelated, right? So we're trying to see what we saw in the sample data to the null and compare that to the null hypothesis of what we would expect to see between x and y, which is nothing. They're not related. How confident do you want to be? That's an open question, and different fields of inquiry have different levels of confidence. Traditionally, in the social sciences, we tend to look for 95% confidence. That is totally arbitrary. Assigning that leads to trade-offs. We talk a little tiny bit about that, but not much. But again, different areas have different levels of confidence, and there are movements within fields and disciplines to change what we should expect for confidence as well. And you'll see that if you read the sort of popular literature on studies that have come back with have been overturned, and it turns out that that sort of level of confidence wasn't sufficient in some cases. Anyway, that's a discussion for a different day. But the norm in most of the literature you will read in political science and social sciences overall is to look for 95% confidence. 95% confidence in the results means if the relationship we observed would have occurred by chance less than 5 times out of 100, we can reject the null hypothesis. So if you get some test statistic and there's only a 5 in 100 chance that that statistic occurred by chance given that null, then we can reject the null hypothesis. Or if there's less than a 5 out of 100 chance that that thing you saw observed in the sample occurred by chance given the null, then you reject the null. If there's a greater than 5% chance that you could have gotten what you got given the null was true, then we don't reject the null. So when we calculate the test statistics, we're going to produce a p-value. The p-value can be used as a simplification to evaluate the null hypothesis. The p-value tells you how confident you are that you can reject the null. If you find a p-value under 0.05, so under 5%, then you will say that the relationship between x and y is statistically significant at the 95% confidence level. If you have a p-value over 0.05, you do not say this typically. Well, you don't say that ever, but you might not say, you might fail to reject the null completely. Occasionally, you will say, oh, well, I might be able to reject the null at the 90% confidence level, but that is a weaker standard. Okay. So again, typically we set our confidence level at 95%, which means our test statistic has only a 5% chance of occurring if the null is true. And then if so, we reject the null hypothesis. Remember, this test statistic is calculated from your sample data. So if the samples you drew produced the outcomes they produced and only had a 5% chance of doing so under the conditions conditional on the null hypothesis being true, then you reject the null. If you could have gotten the data you got at a higher probability given the null was true, you do not reject the null. The goal of all this is to reduce what we call type 1 error. Type 1 error, and people, including me, always mix these up when you're thinking about them. It takes a while to get used to. But type 1 error is when you reject the null hypothesis when it was actually true. So we're trying to avoid rejecting the null, saying that there's definitely a relationship when actually there is no relationship. We're trying to avoid saying there's a relationship between two things when there's not. Right? We don't want these false positives. We don't want situations which we say something's happening, but it's actually not happening. Type 2 error is saying that null is true, accepting the null, when the null is actually false. Right? That's a false negative. That's saying there's no relationship when there actually is a relationship. Neither is good. Errors are usually bad in this context, right? And all tests, like all medical tests you might see, have both kinds of error associated with them, and that can be problematic, right? Different kinds of studies have different trade-offs in terms of increasing one type of error versus increasing the other type of error. Usually you cannot get both well, right? When you try to really bear down on type 1 errors so that you reject a null almost never when it's true, then it's much easier to say the null is true when it's actually false, because you made such a high standard for rejecting the null that you very often will fail to reject the null when you actually should have. So there's this trade-off, and you have to think in your particular context which is more important to you. Okay, a little more about p-values. Again, p-values are the probability that we would see the observed relationship in the sample data if there were truly no relationship in the population. So the probability that we saw a particular observed relationship in the sample data given that there's no relationship in the population at all, given that the null is true. So these p's are probabilities, they go from 0 to 1. And the smaller they are, the more confident you are. A p of like 0.8 means there's a very high chance you could have observed your data given the null was true, so you're just not going to consider your experiment as having rejected the null at all. If p is 0.0001, it is very, very unlikely that you got your data given the null was actually true. In general, the larger the sample you have, the easier it is to get lower p-values, because the larger the sample you have, as you saw before when we took different samples from all the congressional elections, the bigger your sample, the smaller the standard error you get, and so the less chance, the more telling in a way any deviation is from the mean. Okay. The p-values have lots of limitations. And statistical significance, while important, is not the be-all and end-all of everything. For one thing, as we just said, higher sample sizes reduce p-values by reducing standard errors. So effectively, we can get really big samples and get a lot of things to be significant that just aren't that important. So we can kind of manipulate our p-values by getting bigger data sets sometimes. P-values are not comparable in terms of importance. If we get a p of 0.001 and a p of 0.04, the p of 0.001 does not mean that value is somehow stronger, that relationship is somehow stronger than the p equals 0.041. What we're saying is that the p equals 0.0011 is less likely to have occurred by chance given the null, but the p equals 0.011 might be representing a very tiny substantive effect, whereas the p equals 0.041 might be a huge effect, a point we'll get to in a second. None of this talks at all about the validity of our measures. Going back to a discussion of measurement, without valid measures, none of this means anything. So that's an important reminder. But the key point here is the p-value, and another key point, is that the p-value is not conclusive evidence for causality. It is a statement of correlation, of true correlation, and correlation that is not due to random chance. It is not a statement of causality for all the reasons we talked about earlier for why correlation is not a proof of causality. Causality requires correlation, which is why we keep looking for it, but correlation does not prove causality. So all statistical significance does is detects whether or not the change in x is associated with the change of y that is not due to chance. And I mentioned this a second ago in terms of this point over here when they're not comparable in terms of strong relationships. But it's very important to note that statistical significance is not a measure of importance or substantive significance, or really even a measure of association. Significance tests for whether or not the association you saw is likely to be due to random chance or not. Associational measures test substantive connections. If you have a very high correlation between two variables, so they move together very strongly, then you might think there's a very strong relationship between the two variables, even if it's marginally significant. There's barely significant statistically. In contrast, you might have a situation in which you're looking at a treatment control group that differ only infinitesimally in terms of their outcome variables you care about, and yet because your sample size is so big, you get strong statistical significance attached to the difference between the two groups when, well, again, the groups don't differ substantively almost at all. That's entirely possible. So measures of association get you substantive importance. They gauge the strength and magnitude of the observed relationship between x and y, but not the significance, although they're related partially. Whereas significance tells you if the results you got are likely to have come from random chance, but doesn't tell you how important the results are substantively. Okay, that's it for this. The next 3 modules, we'll be looking at squares of that 2x2 table we saw for different types of variables and going through and seeing how to actually calculate statistical significance in each case.